Welcome to our notes for section 6.2. Today we're talking about solving differential equations again, and we're also going to talk about applications of differential equations. Namely, we're going to talk about the exponential growth and decay model. Excuse me. So just like 6.1, the very first thing we're going to start with is just this idea of solving a differential equation by using the technique that we call separation of variables. And we touched on this in the previous notes for 6.1. It's just that in 6.1, they kept it pretty easy where the only thing you had to do to separate your variables, get all your x's on one side, all your y's on the other, was a single step. You had to multiply by dx. Here, we're going to have two steps in order to isolate all the y's on the left and all the x's on the right-hand side. So what I notice is that if I have on the left-hand side, I have this dx. In order to get rid of dividing by dx here, I would multiply both sides by dx. And in order to get rid of the division by y, I would need to multiply by y on both sides. That's going to give me y times dy equal to 2x times dx. Or on this one, actually, you could think about it also as sort of cross multiplication. Once I have all the y's on the left, all the x's on the right, really the constant can go either way. Typically, you'll just leave it where it was, so I'm going to leave it on the right-hand side. Then I would go ahead and integrate both sides. I would get y squared over 2, and let's see, the 2 would cancel with the half, so x squared plus c. And if I wanted to, I could circle the answer right here. Typically on the AP exam, if it's multiple choice, you'll be able to see how they solved it. But they'll also, in the FRQs, give you sort of a hint. So, and I did this on our chapter test too. I added in something that said solve for, and then here I would say solve for c. In other words, I want my equation to read as c equals. If you start to look in the back of your book, you'll notice sometimes they solve for y, sometimes for x, sometimes for c. Sometimes they'll get everything on one side and set it equal to 0. It's hard to know exactly what the expectation is. So I will typically, on the assessments, I will add in this extra little phrasing to tell you how I want you to solve it. So at the end here, I would say, all right, well, let's multiply everything by 2. That'll get rid of my fraction. And let's see, I would get y squared equal to 2x squared. If you double a constant, guess what? You still have a constant. And so I wrote my solution up as c equals y squared minus 2x squared. So sometimes you just kind of have to play a game and see how you can get it to match the back of the book. Again, multiple choice, not an issue. And usually they'll give you some sort of hint on an assessment about how they want you to actually express your final answer. I only put one example here because realistically, it is not that much different than what we did yesterday. They kind of take baby steps here and they're focusing maybe on taking 2 steps to separate your variables, but the process is exactly the same. The rest of our notes are all about these applications, and I think you'll probably be happy because a lot of this is actually pre-calc once we get past sort of the proof of where the growth and decay models come from. So a lot of our applications, you'll read the phrasing that the rate of change of a variable y is directly proportional to the value of y. So the rate of change, that would be my dy. And here we're talking about y being a function of t. So dy dt is, that's my equal sign. And then a direct proportionality implies that there is some sort of constant, we call it the constant of proportionality, directly proportional to the value of y, so directly proportional to y. I can translate that phrasing, the rate of change of y is directly proportional to y, by writing this symbolic notation. That is a differential equation, right? It has an equal sign and a derivative inside of it. So we can go ahead and determine, well, what is the differential equation that would satisfy that relationship? Because you're going to see that statement about direct proportionality a whole lot. Well, we can do separation of variables, right? I'm going to divide my y over to the other side, and that would give me 1 over y times dy. I'm going to leave my constant, my k, on the right-hand side. I don't want to introduce another piece in my quotient, but I will multiply by dt on both sides to separate so that I have y's on the left and t's on the right. Remember, k is just this constant, so really it could go either way. And then I'm going to integrate, right? If I integrate 1 over y, I will have the log of the absolute value of y equal to, and then here I would have k times t plus a constant called c. Let's go ahead and solve this for the variable y. Do you remember how to get a y outside of your logarithm? The trick was to use e and use what's called the one-to-one theorem, which says that if they're equal, if two things are equal, then they would also be equivalent powers for a like base. Remember though, you have to set the whole side as your power. The sides are what are equal, so the sides become the powers. And e to the log would give me my y. We have inverse operations. You might be wondering, well, why do I get to drop the absolute value? Recall that e raised to anything should be a positive number. So the absolute value gets sort of taken care of by raising it as a power of e. On this side, I would have e, and remember, you add powers if you're multiplying like bases. So watch this trick. Instead of writing e to the kt plus c, I'm going to write e to the kt times e to the c. Still equivalent, because if I wanted to put them back together, I would add the powers and I'd be right back where I came from. And then I can rewrite this one more time. E is a constant, c is a constant. A constant raised to a constant will be another constant, so we'll have c times e to the k times t. This should look familiar to you. It is our exponential growth and decay model. You guys learned it last year in honors pre-calc or pre-calc. You learned it probably in algebra 2, maybe even algebra 1, I'm not sure, as the exponential growth and decay model. We just never explained where it came from. So now we have the calculus behind where this is coming from. The best part about this model is that once you have established this exponential growth and decay model, if you read this phrasing up here, rather than starting here again, we will accept that knowing that the rate of change is directly proportional to the value of the function implies that we have exponential growth or decay. And we will just jump straight from having that phrasing about the rate to knowing and accepting that this is an exponential growth model, and we can skip over the calculus. So that said, let's flip the page and try some out. So for example, I'm reading this first example here. The rate of change of y is directly proportional to y. I read that, and I know that I could write it just like I did on the previous page, that dy dt is equal to k times y. However, because of the work we just did together, we are going to jump straight to the phrase or to the symbols y equals ce to the kt. You do not need to redo the calculus every time. You already know that it is true. They've given you some data points. So when t is 0, y is 2. If t is 0, then you would have y equals c e to the 0. So if y is 2, then 2 is equal to c times 1. C is 2. Your c, your constant, I don't know if you remember this from your days of studying exponential growth and decay models, but that corresponds to your initial value. So realistically, you could have just read that little statement about t being 0, and you could have said, well, I know then that c is equal to 2. So we can do a little bit better with our model, right? And we can write the 2 there. Why do I have another data point? Well, I'm still missing the constant of proportionality. I need to find what k is. So I'm going to plug in the second data point. I know that I should be getting 4 when I plug in a 2 for my t value. Now you need to solve for k. You want to isolate your exponential first, so I'll divide both sides by 2. Some algebra review here. And then do you recall how to get the k out of the power? The trick is to use logarithms, the log of 2 and the log of e to the 2k. On the right-hand side, the log of e, that will undo one another. Log of e is 1. The 2k comes forward as a coefficient, and log 2. So k is equal to log of 2 divided by 2. That means that my model would be y equals 2. That was my initial value. E, the k value is log 2 over 2, and then times t. So that is the specific model for the scenario given here. How am I going to find the value of y when t is 3? I'll plug it into my calculator. So y of 3, when I'm plugging in 3, I get 2e to the log 2 over 2 times 3. And you're going to want to double check that you know how to do order of operations. Type it into your calculator. I would advise taking log 2 over 2, multiply that answer by 3, e to that power, multiply by 2. Watch your order of operations. You should be getting 5.65, and AP would either accept a 6 if you do what's called truncating and just cut, or you could write 5.657. I would encourage you to start paying attention to those details. Always 3 decimal places. You can either truncate or you can use sort of the scientific method of rounding up if it's 5 or larger. They'll accept either form of rounding. But you do need to go to 3 decimal places in this section. Radioactive decay, this is another one. It's basically the same thing. If you know that you have radioactive decay, you know that you are following an exponential decay model. So instead of starting over with the calculus, you can just jump straight to the decay model. Let's see. Suppose that 10 grams of the plutonium isotope were released in the Chernobyl nuclear accident. How long will it take for those 10 grams to decay down to 1 gram, knowing that the half-life of our plutonium is 24,100 years? So let's see. The initial value, right, C at time 0, I know that I am starting with exactly 10 grams. Now, they didn't give me another point the same exact way that they did it in the first example, but they kind of did. If they tell you one half-life is 24,100 years, then how much plutonium is left over after exactly 24,100 years? Well, for this sample, I would have exactly 5 grams. So let's see, 24,100 times K. And that extra piece, that data point about the half-life, will be enough for me to find my K value. The method would be the same as above. I would want to divide out to isolate the exponential. So 5 divided by 10 is a half. That would be e to the 24,100 times K. I would take the log of both sides, so that's the log of 1/2 equal to, when I take the log of e, that's going to disappear. That is an inverse function. And so my K value is the log of 1/2 over 24,100. Now you want to be careful in calc not to round here. I don't want to get a decimal equivalent and round too early, because their methodology has you only rounding 1 time at the very end of the answer. What you can do, because this is kind of a bulky, annoying thing to write out, you can go back, and now that you have said what K is equal to, you have made a note of what K is, then you can continue to just write K instead of writing the whole thing. Okay, so as long as you have stated exactly what that value is, you can keep calling it by sort of its nickname. Let's see, I would like to know how long it will take. So that's a time question. T is my variable to get to 1 gram. So when will I have 1 gram from that original 10? And remember, I know what K is now. So actually the same process, I would divide by 10. That would give me e to the K times T. I would take the logarithm of both sides. That would release the K times T from the power. Recall, K is something I know. I'm solving for T, so I need to divide. My T value would be the log of 1/10 divided by K. And then double check, type this into your calculator, pause maybe for a second here. You should be getting an answer of 80,058.467 years. A very, very, very long time. Example 3, a little bit harder. If we read, they didn't give us an example 3. They did not give us the initial value. They started with 2 data points, neither of which is at time 0. So suppose an experimental population of fruit flies increases according to the laws of exponential growth. You had 100 fruit flies after the second day and 300 after the fourth. How many fruit flies were in the original population? So what are we going to do? Well, it's population growth. We are assuming population growth is exponential, so we are going to jump straight to our exponential growth model. Think of these as 2 data points. I know that on the second day, I should have 100 flies. So that would mean that I will have 100 flies when t is 2. And I would have 300 flies when t was 4. Problem being, I don't have k and I don't have c. I do have a 2-variable, 2-equation system, and I need to solve a system of equations. There are multiple ways of doing this. It's just either substitution or elimination. There's a couple ways of doing that. I'll show you the substitution method. It works out very nice here. So let's look at the first one, and we are going to solve for e to the 2k. That would be 100 divided by c. I don't want to go all the way down to solving for k. It would get pretty messy here. But a neat trick, e to the 2k squared would be e to the 4k. So I can use that to rewrite the second equation. That would be 300 equals c, and then e to the 4k would just be e to the 2k squared, right? Power to a power you multiply, so e to the 2k squared would be e to the 4k. That would mean that I could substitute in 100 over c squared. Right? This kind of depended on me having a 2 and a 4. There are other ways to solve this. Make sure that you try them out and see if you can create your own model this way. What would happen? I would have 300 equal to 100 squared, so that's 10,000. There's a c here over a c squared, so that would give me over c. And I would cross multiply or multiply both sides by c, and I will have that c equals 10,000 divided by 300. I'm solving for that initial value, so the nice thing here is I've gotten directly to my solution. Now, they would probably add something in here round to the nearest whole number because population is a little bit tricky. So let's add that in. This comes out to be about 33 flies. And I did not put that in the original statement, so if you told me 33.333 flies, that's fine too. But we'll say 33 flies for the original population. All of those are exponential growth and decay, the traditional models, what you know and love. Newton's law of cooling is another very standard application, and unfortunately, it is not the same as the direct proportionality of population growth or decay. So we want to look at Newton's law of cooling as sort of a separate question from the rest. It states that the rate of change of the temperature of an object is proportional to, so I still have the temperature. Let's call that y. I don't want to use t for temperature because there's also t for time here. So let's say that y is the temperature of your object. In this problem, if I keep reading, it's my coffee. And t is going to be my time. The rate of change of the temperature of this object, so dy dt, is, and then directly proportional to, or proportional to. And then the difference here is that it's not directly proportional to a single variable. It's proportional to the difference between the object's temperature and the temperature of the surrounding medium. So if my coffee has a temperature of 100 degrees and the room is 60, right, we're going to assume that the coffee is going to change, not the room. The coffee is not warm enough to warm the room. We would write this as y, the temperature of the object, the difference, so subtract the temperature of the surrounding medium, so 60 degrees. I have a different original proportionality statement, which means that I am, unfortunately, going to have to restart the process. I'll separate my variables, and then I will determine, with Newton's law of cooling here, that I will determine a different proportion or equation. So that would mean that I would divide by y minus 60, so 1 over y minus 60 dy. That isolates my y's on the left. I'm going to keep my k where it's at. and pull my t's to the right-hand side. So I have isolated the y's and the t's. Remember, k is a constant, so it can go either direction. I'm going to integrate. Just like I did on that very first page, I just happen to have a different relation here. So this would be the log of the absolute value of y minus 60 equal to k times t plus c. Just like, again, on the first page, I will use my exponents to come up with an equation for y equals so that I can have this in relationship to the temperature of the coffee. So that would give me y minus 60 is equal to, let's see, c times e to the kt. Recall that this would be e to the kt times e to the c, and that's why my c becomes that multiplier. So the temperature of my coffee would be 60 plus, and then the relationship is still exponential, but it's slightly altered from that original exponential growth and decay model. So what can I do with this, right? I want to know if after 10 minutes my temperature was 90 degrees, how much longer to get down to 80 degrees? Well, we need to get some specifics for this particular model. Now be careful, this is no longer the same model, so I actually want to go ahead and solve for C. I do have a data point. It took me 10 minutes to get to 90. So, oh, sorry, I should start here. Initially my temperature, T equals 0, my Y value was 100 degrees. So that would mean that, I'm going back to this equation, 100 was 60 plus C, e to the 0. Right? If my time is 0, then this power becomes a 0. E to the 0 is 1. And that means that C is 40. With Newton's law of cooling, I need to be careful. It's not just the initial value, that difference between. So that gives me a slightly more specific equation, 60 plus 40 e to the k times t. And now I'll use the second data point, right? If after 10 minutes my temperature was 90 degrees, then I could plug in a 90 for the temperature, 60 plus 40, and my t being 10 minutes in, that's going to give me, e to the 10 times k. So I'm going to isolate my variable first. I would need to subtract the 60. That would give me 30. But then I would divide by 40, and that is e to the 10 times k. Take the log of both sides. So log of, let's rewrite it as 3/4 because it's a little shorter that way. And log on this side would release just the 10k out of the power. So my k value, that constant of proportionality, is the log of 3/4, all divided by 10. I'm going to just refer to it as k again, but now, sorry for the short space here, but we can actually write up the specific formula that would model this scenario. It would be that, let's see, 60 plus 40 e to the k times t, where k is the log of 3/4 divided by 10. I want to know what's it going to take to get down to 80 degrees. So I know I want an 80-degree coffee. I've got 60 plus 40 e to the k times t. Remember, I'm solving for a time, so t is my variable. Subtract the 60, that's 20. Divide the 40, that's half. And that would isolate the exponential, at which point I'm taking the log. And I can go ahead and solve for my time by taking the log of a half and dividing by that k value. At that point, I would go ahead and compute k first. I would take then the log of a half, divide by that number. You should be getting, again, double check that you know how to actually compute, because it's a calculator question, but trust me, kids make all kinds of issues with it. 24.094. So in the 24th minute, I will be down to 80 degrees. There is one glitch to this question. Always go back and reread your question. How much longer? So after 10 minutes, I got to 90. How much longer would it take me, to get to 80? So it's going to take me 14.094 minutes longer. Gotta wait about 14 more minutes to drink my coffee at that perfect temperature. So anyways, most of the questions are exponential growth and decay, and you do not need to go through this whole process every time you're using that traditional model. You would need to redo the process if you have any sort of statement that gives you a different ratio for your proportionality. Work through them, use the rest of the hour to do so, and tomorrow we're moving on to the last section. Chapter 6 is flying by. We'll see you then.